Hi students, Professor Nugent here. In this video we're going to discuss some of the nuances of fixed effects and one more assumption. The additional assumption is the seventh assumption in addition to the six assumptions we have already discussed. This seventh assumption is the normality assumption. Conditional on xi and ai, the idiosyncratic error UIT is independently and identically distributed normally with a mean of 0 and a variance of sigma squared u. So the seventh assumption implies the assumptions 4 through 6 that we have already discussed and gives us exact t and f distributions for our inference procedures. Without this seventh assumption, we'll need to rely on large sample approximations so that our t statistics and f statistics, they're not going to be exact, and we will need large samples to make good inference. So we don't need the seventh assumption, but it helps us with our inference. All right. So that is it for assumptions. Let's move on to some nuances and we'll continue discussing some implications of the assumptions. One of the things we want to discuss is with the first assumption, we wrote down a model that is multivariate. Right? But the way that we derived the fixed effects model was univariate. So it is perfectly fine and easy to derive the fixed effects model that is multivariate. And this simply requires the meaning of all the explanatory variables. In the same way that we started our first video on fixed effects. Okay. Let's talk about assumption 4 a little bit more. So estimating the fixed effects equation, we'll call that the fixed effects equation. We wrote this down as the demeaned equation YIT is equal to, we have beta 1 x1 it, and this is the univariate case. We can write this in terms of the multivariate case plus beta k xk it, so this is beta x1 it xk it plus uit. So this, where the two dots above the variables represents the demeaned data, estimating this equation using pooled OLS requires strict exogeneity for unbiasedness of the coefficients. Now, what is strict exogeneity? That is our fourth assumption, the expected value of UIT given xi ai is equal to 0. So for each t, the expected value of the idiosyncratic error given the explanatory variables in all time periods and the unobserved effect is 0. So we need strict exogeneity. We say that this is strict because this relationship implies for all time periods. For all t, okay? So we have that the idiosyncratic error should be uncorrelated with each exponential variable across all time periods. And this is different from the first difference estimator, which you will see in some derivations only requires exogeneity across adjacent time periods. Alright, so in our derivation, as we have previously discussed in chapter 13, anything constant over time this will drop out. By mean differencing. Right? Because we are using the variation over time to identify the coefficient. And so if there's no variation over time, then there's no variation with which to identify the coefficient. And so, in effect, those variables that do not vary over time drop out of the equation. And this is a result of the way that we remove AI. Because AI is constant over time, then we go about some different ways of removing that constant, but that also removes all constants over time. So it's this as a consequence removes any kind of variables we want to include in our equation that are constant over time, such as things like race or gender, so on and so forth. All right, let's think about some more nuances of fixed effects. We lose 1 degree of freedom by mean differencing. And that is, we have that per time period. Rather, that's per cross-sectional unit. We lose 1 degree of freedom. We also lose, if we have included an intercept in our population regression function, we lose that by mean differencing too. So the resulting degrees of freedom are nt minus n, so we subtract n because we lose 1 degree of freedom per cross-sectional unit, and there are n cross-sectional units, minus k for k parameters. And we don't have that intercept, we're not estimating an intercept. So this is our degrees of freedom for the fixed effects model. The interpretation of the coefficients is the same as we would interpret normally, or as we have been interpreting the coefficients. With the caveat that the coefficient has been identified using within variation, and that is the variation of the individual units over time. Okay, so we will go about the same kind of interpretation, but we need to keep in mind what variation we use to identify that coefficient and what that means. And we'll think about some examples of that during our synchronous meetings. there are other nuances of using the fixed effects estimator. So R squared is an imperfect goodness of fit measure. This represents the amount of time variation in YIT that is explained by the time variation in the explanatory variables. Okay, so it's imperfect. We can use it for now, and we may think about some other goodness of fit measures later. While the time constant variables cannot be included in a fixed effects regression, we can include interactions between a constant and a year dummy. And if we do that, then what we get, having left 1 year out, is how the effect of the constant changes with respect to the base year. An example of this might be including gender in a wage equation, interacting that with year, and then you get how the gender wage gap changes with respect to the base year. And finally, the errors are likely to be serially correlated. So recall that this we assumed through assumption number 6 that for t not equal to s, the idiosyncratic errors are uncorrelated, but it is likely the case that assumption 6 is not true, that the errors are serially correlated, and we can fix this by clustering. Okay, we can fix by clustering. Well, we're not fixing the serial correlation. Rather, what we're doing is calculating standard errors that are robust to serial correlation. So the standard errors in large cross sections based on, we calculate standard errors in large cross sections based on the weakest set of assumptions that are valid in the presence of serial correlation. And we can do this in Stata following the regression command with cluster ID. And we will do this in our Stata tutorial.